Okay, so here's the theorem that we just talked about. And here is the corollary of it, establishing that the monodromy map between three images of pi is a bijection. So what we'll do is produce an inverse to that map. That's one way of showing that a map is a bijection. So, and producing an inverse amounts to producing a map the other way, and then checking that each composite, first one way, then the other, and vice versa, is the identity map. So let's first figure out what that map the other way is. Well, I indicated it before. This monodromy map is induced by a path in the base. There's an obvious path going the other way, given a path. It's the path where you read time backwards. So I'll write that as gamma bar. It's a path, in other words, continuous map from 0, 1 to b, that first precomposes by a map from 0, 1 to itself, given by t goes to 1 minus t, followed by the original path gamma. So there's a sense in which that path is inverse to gamma. Namely, if you do gamma and then do this gamma bar, you just trace out a path in the base and then trace it exactly backwards. There is a homotopy, in other words, a continuous map from the interval across an interval, so that when the first parameter is 0, the path in B witnesses go by gamma and then go back. When that parameter is 1. And when it's 0, it will be the constant path at the starting point of the path gamma. And for all s's in between, you'll just trace out the path to some moment, stop and wait for a while, and then come back. So here's a formula for what such a map H is. It's a path of paths, which at time 0, evidently, if you look at this expression, is the constant map at gamma of 0. And when s is equal to 1, the resulting path in B is the path that traces out gamma and then traces gamma backwards. And for all s's in between, it just traces out gamma to just for a little while and then stops and waits and then comes back. So that's H. So look, we have this commutative diagram now. H is the map just constructed into B. The path which traces out gamma and then traces by gamma bar describes a map from 0, 1 into E. I messed up these things. So the solid diagram commutes. We have this path of paths and a lift of that path of paths at time 1. Now, by this theorem, the unique homotopy lifting property, applied to where capital P is a closed interval, I kind of got messed up on which factor was which here, you can see, and also between 0 and 1, 0 versus 1, but those are inconsequential. So the homotopy lifting property guarantees exactly a unique lift here. And what is that unique lift? Well, it's for each S in here, this unique lift selects out a path in capital E, and as you vary S, that witnesses a path of paths in E. In other words, a homotopy of paths in E. So what that gives then is that the composite of monodromy maps, first gamma shriek followed by gamma bar shriek, is homotopic to the unique lift of the constant path. But that's just the constant path. So this constant path, lower shriek, is just the identity. So we see that this composite map of sets is homotopic to the identity map. We want it to be equal to the identity map in order for gamma bar shriek to be an inverse to gamma shriek. But to have a homotopy between two continuous maps to a discrete topological space is just to say that those two continuous maps, in this case this one and identity, are equal. So that's what's written here. And now, obviously, there's a symmetry, you can swap gamma and gamma bar in this argument to get the reverse identity. And that's how we conclude that gamma lower shriek is a bijection as desired. So this monodromy map is indeed a bijection. So this is cool. Think about it in the examples. Which I'll reserve for the exercises, what this monodromy is. But even just pause or think about it right now, what this monodromy map is in the case of S2 mapping to RP2. That's interesting to think about.